Anybody know what the E is? Let me see what's happening in the chat here. No, nobody seems to know what E is. All right. On your calculator, I don't have the virtual calculator on this device. I've changed devices. On your calculator, there's a key there that has an E on it. And it is a constant, just like how pi is a constant. It's a constant. And it's been attributed to somebody called Euler. This is not a history class, but I'll just sort of tell you a little bit about him. Swiss mathematician, and made a lot of contributions to math. Helped to popularize the use of pi and also the symbol I to represent imaginary numbers. But he also developed the irrational number E. So irrational, let me just remind you, means natural number. Okay. Is it f of x? Well, it's when you say if it's f of x, it's a constant. It's a number, right? It's not really a natural number either, Richard, because natural numbers are usually like 1, 2, 3, 4, 5, whereas this is a decimal. And not only is it a decimal, but it's one of these things like pi, which cannot be stated as a fraction. There is no way to state as a fraction. A number like 0.33333, although it's a decimal, and although it is it's a number that goes on forever, right? It's not irrational because 0.333333 can be written as 1 over 3, right? So that is that it goes on forever, right? Non-terminating, as they call it, doesn't make it irrational, right? Because numbers like 1 over 3, when you put them as a decimal, they are non-terminating. What makes it irrational, such as E and such as pi, is that it's also non-repeating. There is no pattern to it. So if you try to, I know when you were, I know when I was younger, they taught me that pi was 22 over 7 or 3 and 1/7. It's not. That's an approximation for pi, but it's not actually pi. So x is a variable and e is a constant. Absolutely. Absolutely, Danny. X is a variable, e is a constant, right? Remember, pi is a number. Pi is not just, although you use a symbol to represent pi, it's not like an x or a y where it's a variable. It's an actual number. It's just that it has several decimal places to it, and nobody has actually worked it out to its full accuracy. There are people in some lab somewhere on a computer right now cranking out some more digits for pi, and they're probably doing the same thing for Euler's constant for the value of e as well. So if you look at the screen, you'll see that it says it's an irrational number. Let me give you a couple of digits here: 2.71828. 1828459. No, there's no pattern. It's not like it's 1828, 1828. It does literally non-terminate, goes on forever. All right. So that's the first thing that I need to make you aware of. But where does it come from and why is it so important in math? Well, it comes from this, right? It's a limit as, and we talked about limits before. It's a limit as x tends towards infinity for this function, 1 plus 1 over x to the power of x, right? So if you were to graph it, which it is on this screen here, right? This is the graph of the function f of x equals 1 plus 1 over x to the power of x. Then you'll notice that it has an asymptote, a horizontal asymptote, and the equation of that asymptote is y equals 0.271828, and all the stuff that we talked about, y equals e. In fact, you can see on the side here that this is what I used to generate this horizontal asymptote, y equals e. So the function does trend towards it from on the left at minus infinity and trend towards it from positive infinity on the right. Okay, so it is in fact, okay, Ella is now checking in. All right, let me just get Ella in. And I'm going to have to mark you late. I'm sure you know that. And we're still hoping that Jessica will show up to complete the full attendance for the class. Okay, so back to this. So that's what E is, right? E came from what I just showed you. I'll go back again. E came from this limit. You've noticed that when you graph this function, that as it moved towards infinity or minus infinity, it tended towards a value 2.71828, etc., etc. But it actually has more significance than that in math. Let me give you one other equation that I was fascinated with when I was learning calculus for the first time. That's this function. the x root of x. So x to the power of 1 over x. For some reason, I started playing around with this function and noticed that this function reached its maximum x value when x is equal to e, 2.71828. And one day during this unit, I'll walk you through how you can actually use derivatives to come up with why that is the case, right? I didn't figure it out until a couple of years ago after I left school, I'll be honest with you on that. So this function actually has its maximum, right? It has a horizontal tangent when x is equal to 2.71828. So the x root of x. So that's another way that it does tend to pop, sort of enter our mathematical world. Whether you want to look at the one I was showing you before, just 1 plus 1 over x to the power of x, or the one that I became obsessed with at one point when I was learning calculus, was the x root of x, which does in fact have a maximum point here. Okay? All right. Let's review a few things from advanced functions that you're supposed to know. The inverse of the exponential function, right? Remember, exponential function is like this. What makes a function exponential is the fact that the variable is the exponent. So you learn about exponential functions that had bases like 2, for instance. So if f of x was equal to 2 to the power of x, then the inverse of that function that I'm pointing to right here would be the base 2 log of x, or you're supposed to have learned that when you were in advanced functions, right? So if 2 to the power of x is the original exponential function, then the inverse of that function, you know what an inverse function is, which takes you the other way, or it's like you reflected across the y equals x line, is the base 2 log of x. So what that means is that the inverse of the exponential function, so e to the x, where e, which is the base that we just talked about, 2.71828, the inverse of that is the base e log of x, but we have a special log key for that on every scientific calculator, and we refer to that as ln of x. So if you look at your calculator keypad right now, probably right beside the log key, you'll see an ln key. Look for it right now. It's right there on your calculator keypad. So we refer to that as the ln of x. And all that means is that we're using the base e for that particular log. So you can use any base for a log, as you know, as you learn in advanced functions, right? I can use a base 2 log. The key on your calculator, right, which has logs on it. Does anybody remember what log that is? Sorry, what's that for? What is the ln key? Well, remember you did logs in advanced functions, right, Adam? The ln key. Okay. Remember we did logs, or you did logs in advanced functions. You remember that? And it was relevant. Yeah, it is quite relevant actually. So back then, when you were doing logs, the teacher probably told you, if you're in my class, I would have told you this, that the log key on your calculator is a base 10 log key. Right? So if I use that key that says log on it, that's a base 10 log, right? But the ln key, which is beside it, usually beside it, again, it depends on the calculator, obviously, but the calculator that I have, it's right beside it. That's my caster right here. So right next to the log key is an ln key. That means that I'm talking about a base e log. So instead of base 10, which is what the log key on your calculator is, the ln key is a base e key. Okay, so that's all that is. We call it, and it's referred to as the natural log. So that's what it's called, as if the other log is unnatural. I don't know why they call it that. It's referred to as a natural log, and it's referred to as sometimes pronounced as ln x. So when you hear somebody say ln x, L-A-W-N, or pronounced the ln, phonetically pronounced that way, they're referring to the base e log of x, is basically what we're saying. All right, hopefully that's clear so far. All right, so just to sort of refresh your memory a little bit, and I'm not using the cursor much, I'm just sort of using my mouse clicks here to go through this. As you can see, it's a PowerPoint presentation. The base 3 log of 81, let's just say that's equal to x because we don't know what it is yet, right? If we say the base 3 log of x, then another way of saying it exponential, this is the logarithmic form of it, is to say 3 to the power of x is equal to 81. Right? That's another way to say it. So this line here that I'm pointing to, right? That's the logarithmic way of saying it. This is the exponential way of saying it. 3 to the power of x equals 81, which means that x is equal to 4, by the way, right? So the base 3 log of 81 is 4, because if you set the base 3 log equal to x and then you write it in exponential form, then x would be equal to 4, because, of course, 3 to the power of 4 is equal to 81, all right? So by the same token, if I asked you for the base e log of 4, then I could set that equal to x. Then I could put it in exponential form and say e to the power of x is equal to 4. And the answer to that is the base e log of 4 is there for whatever the ln of 4 is. So using, remember, once I talk about base e log, it means I'm talking about the ln key. So right now I'm talking about the log base e of 4, which is some weird number, 1.386, goes on forever. Which does mean, though, that if I were to raise e to the power of this thing, I'm going to get approximately 4, right? Because if I put this in exponential form, it would be e to the power of this number that gives me that 4, right? Remember, a log, and I've said this to my class when I was doing advanced functions with them, think of a log of it as an exponent. So if the ln of something is this number, then that number really represents an exponent on the base of e. Just as how this 4 represents an exponent on a base of 3, if it's a base 3 log. Okay, so that's all that this e is all about. So just to remind you that exponential functions and log functions are inverse of each other. You can actually represent them on a graph as a reflection across the y equals x line. So this would be my e to the x line right here. This is the exponential function right here. The black line that's rising as you go from left to right, that's my exponential function. So if I reflect that across this dotted line right here, then this function on the other side of that is the ln of x, so the base e log of x line. Okay, so that's all that is. All right, now I hope everybody has found the ln key on their calculator. I hope you have all looked for it. Can I just get a reaction from the room on that? Has everybody found the ln key? Because you will need to be able to use that ln key from time to time. Perfect. Okay, when we're doing the stuff that we're doing right now. So as long as you can find it, you can use it. Let's move on. So we need to figure out what the derivative of of e to the x is. So in Desmos, you'll notice that I have already shown you what the e to the x function is. So f of x equals e to the x. That's this function right here, right? It's an exponential function, like I said before. And in my second line, and you probably didn't know that Desmos could do this, and probably I shouldn't tell you that Desmos will do this, I can actually get Desmos to draw me the derivative function. So f prime x would be the derivative function. So I'm going to press this button now. And what's going to happen is that rather than me going up to Desmos, I thought I'd just do a little graphic here. What's going to happen is that you're going to see me pressing the button for the f prime of x function to appear. So I want you to compare the two things. I'm going to press this and watch what happens when I activate the derivative function for the e to the x. So e to the x is the one that you're seeing right now. And the graphic is going to show you what happens when we superimpose on that the derivative function for e to the x. So here we go. What did you just learn? What did that little movie, okay, it's movie time, no popcorn involved, right? What did you just pick up from what you just saw? What's the derivative of e to the x? They're the same. Correct. That's exactly right. The derivative of e to the x, it's right there. Oh, sorry, need to go back. The derivative of e to the x is e to the x, right? The original function e to the x, when you derive it, gives you the function e to the x. All right? Derivative, as you just said, Jordan and Ashvan and Ariana are the same. Okay, that's interesting. So let's see what we can do with that then. Let's take this and try to derive it. Now, think of this as being a function of a function. So you're taking e to the 4x, right? So the base is e, and you're raising that to the power of an exponent of 4x. Well, it is what you hopefully would expect. If we were to write this as e to the power of u, where u is 4x, then think about when we're doing the chain rule, back when we started looking at derivatives, I don't know, maybe about a month ago. So what I'm going to do is I'm going to use this dy dx to be dy du times du dx. I'm going to find the derivative with respect to u first, this function, and multiply it by the by the du dx function. All right, so what does that look like? It looks like this. E to the power, so dy du of e to the u is e to the u, and du dx is 4. So I'm just going to multiply those two things together. So the result of that is this. dy dx when you multiply those two together, is just simply e to the 4x multiplied by 4. So the e to the u part is the e to the 4x, and you multiply that by 4. It's really that simple, right? So you basically repeat the function itself, which in this case is e to the 4x, and then multiply it by the derivative of the top. The root of the top is 4. That's it, done. We've just derived our first exponential function, right? And of course, you could write the 4 in the front. That's obvious, right? So all I've done here is I've just put the 4 in the front of the function. All right. Here's another one. This time, we're talking about a product. So we're going to treat this like we treated every other product for differentiation. So u dv dx plus v du dx. If you remember that from our stuff with exponential functions, sorry, with regular derivatives, that should hopefully make sense. So I'm going to first of all use the product law, like I said, and I'm going to have 5x4, so that's the derivative of the first part right here, multiplied by the underived second part, so that's the e minus 3x squared, so that doesn't change. Then I'm going to derive the second part, which means I'm going to still have the same e to the minus 3x squared, times the derivative of the exponent, which is the minus 6x, times the underived first part, x to the power of 5. All right, there's your product law at work. You might want to rearrange that a little bit. Maybe putting the put it. This is a minus, so you might want to make this minus 6x6 because these two can be multiplied together. The minus 6x and the x to the power of 5 to be minus 6x6, but you still have the rest of the stuff that's there as it was. Okay, so there is your derivative function of that original x5 e to the minus 3x squared. Again, stop me, slow me down if needs be. If anything I'm doing is going too fast for you, just stop me. See, I'm not even using my cursor today or my stylus today. I'm just simply going through the steps in the PowerPoint presentation. All right, but I can certainly stop and go through something else in more detail, go through anything else in more detail if I need to. All right, and of course we could also, many times factoring is not a bad idea. So the common factor between these two is the x to the 4e to the minus 3x squared. That's a common factor between these two. And then you'd have this left. And I would expect you to try to do that because sometimes you have to set something equal to 0, that having this form here makes it easier for you to be able to figure out where the horizontal tangents are. Okay, can I explain the x of 5 at the end? I sure can, Kushi. Okay, at the end, let me just make sure I got your question right. X to the power of 5 at the end. At the end. Oh, at the end here. Okay. So remember, that's the part, first step. You did say first step. Let me grab my stylus for that. I'm going to take you back to when I'm going to fold this over here. I'm going to take you back to when we were doing derivatives first. If f of x was equal to the product of two functions, so let's say it was a times b, then the f prime of x was equal to the derivative of a, so dA dx times the b, right, with the underived second part, plus dB dx times the a. Does that, okay, I know the writing is not great, but do you remember that from when we were doing the product law, Koshi? Okay, so that's what we're doing here, right? I'm going to point to it now. We take the x5 and we derive it, which gives us the 5x4, okay? And then we multiply that by the underived second part. So the underived second part is e to the minus 3x squared. Plus, now we're going to derive the first part. The first part is, sorry, the second part, derive the second part. So we're going to take the e to the minus 3x squared, write it again, because the derivative of that is just the same thing, but then multiply it by the derivative of the exponent, which is minus 6x, then multiply it by the underived first part. That's where that x to the power of 5 comes from. Does that make sense, Kushi? Right, remember, you don't put the derivative of, right, okay. All right, so let's move ahead. If that hopefully made sense, let's keep going. Then this last step here is just a factoring. That's all that is. Let's try to differentiate this now. Again, it's a product, right? It's a product of two things. There are actually two approaches to this. And I think, if I remember correctly, setting us up, I did this both ways. What do you think I'm going to do next? If you had to do this, what would you do next? Right? Can anybody give me an approach to doing this that they think might work? So e to the power of x times e to the power of 4x. What do we do here? Product law, Adam says. Okay. Any other answers apart from what Adam just said? Is it the product law that we're going to be using here, folks? Come on, I need some more reaction from the room here. Okay, Sarah says product law as well. Yeah? Okay, product law. Product law all the way. Interesting. Does that look like that makes sense to you? Look at what I just wrote down. What do you think I just did? Anybody? You see what I just did there, folks? Ah, what did I just do? I just simplified it. Right? I don't know how to multiply the exponents. I add them together, Tamaleo. When you multiply two things that have the same base, we add the exponents. So, no, we can use the product law. Okay, don't get me wrong. We can use the product law. But, and there's always more than one way to do everything in math, as I've already said several times. But if I just use this approach, then I would get this. 5 times e to the 5x, plain and simple, right? And that's because it would be the e to the 5x multiplied by the root of the inside of that part in there. So I think that if I had that to do, I wouldn't use the product law. I would find that little shortcut way to do it if I were you. That's just my, and I'm always looking for shorter ways. Yeah, we can go back and use the product law, but why would you if you don't have to, is all I'm saying, right? Everybody with me on that? Let me do a quick check-in of the room. I like to do that. Can I go back? I sure can. I sure can. No, if we had used a product law, we could, let's see what happens if we use a product law then. So let me fold this up back again, because if I'm writing on the screen, I would prefer. So if I was using a product law, then I'm going to take the first one and derive it, which would give me e to the x, and multiply it by the underived. So remember, that's not being, e to the x, when you derive it, just e to the x. Okay? Would it be 5e4x? That's what it says. 5e. Oh, 4x. No, not 4x. No, not to the 4x. Not at all. Not at all. But let's keep going and see what happens. Let's derive the first. So I'm deriving this first. I'm still going to be e to the x multiplied by the underived second part, which would be e to the 4x, plus, let's now take the derived second one, which would be e to the 4x multiplied by 4, multiplied by the underived first one, which would be e to the x. So far, so good. Does that make sense? Jordan, am I recording today? Yes, Ariane, I am recording. Okay. So let's put these two together now. Wouldn't this be e to the 5x? Wouldn't that be what that is? Yes. And then the second one would be, again, adding these together, it would be 4 times e to the 5x again. Do you see that? Does that make sense? Those two together? And then those are like terms. So that would be equal to 4. Sorry, 5. Sorry, 5 e to the 5x. Is everybody on the same page with me on that? Does that all make sense? In part, sorry about my bad writing there. Okay, it's the same answer. Obviously, it has to be the same answer because it's just different routes, but the derivative will still be the same no matter which way you do it. Clearly, what I did made it faster, but you could use a product law. The product law is going to give you the same answer eventually anyway. All right, let me do a quick check-in here. I like to sort out, make sure that everybody is with me on this. Christopher and Danny, did that make sense? Christopher, check in for me, please. And Danny, check in for me, please. Okay, and Danny, are you there? Where's Danny? What happened to Danny? Where did Danny go? Danny, I need to hear from you. All right, Danny is not there. That's not good, Danny. Need to hear from you when I call on you. All right. All right. So, Danny, I'm going to be calling on you again in a couple of minutes. Hopefully, you're going to be there when I call on you the next time. All right. So, hopefully, that made sense. We're going to continue from there. So, let's try this one. Selecting a strategy to determine the value of the derivative. So, what we're asking for is what is the value of the function when you derive it and put -1 into it. It's basically what we're saying, right? So let's do the derivative. Well, that's just a coefficient, folks. That's all that is. So I'm gonna treat it just as if the 3 was on the outside and we don't really need to care. We don't need to really do anything with it much. I'm gonna derive this as 3. Oh, I don't need to do that. I have it all set up here. Okay, I see a hand going off. Danny, where were you? I was calling for you just now. All right, remember letting me know when you're leaving. Okay. All right, so let me just click my little mouse here, right? And you can see that the derivative of that is 6x e to the x squared. Now, hopefully everybody's okay with that, right? You're going to multiply the inside root, which is x squared, and the derivative of that, of course, is 2x. It's going to be 2x times that 3, which gives you the 6x. So it's 6x times e to the x squared. All right? Is that good with everybody? Does that derivative make sense to everybody? Okay, Adam says yes. That's good. Is it only Adam that makes sense to? Where did you get the 6x from? Okay, so let me grab the stylus again. When you have a coefficient on a derivative, you can leave the coefficient out until the end. So just think of the 3 as being somewhere out here. Let's just derive the rest of it. So it's going to be e to the x squared. We're not doing anything with that. Multiplied by the 2x. Right? Well, doesn't that 2x and that 3 give us the 6x and then times e to the x squared after that? All right. Does that make sense now, Taj? And Anika, you're okay with that? Does that make Taj? I want to make sure. Okay. So that 3 in the front. Anytime you have any coefficient on any function that you're going to find a derivative, just put the 3 on. Just put that on the side because the 3 can come in later on. Okay. It's not like a product or anything. It's just a coefficient. You're welcome. All right. So there's our function, and what we're trying to do is find f1 of that. So if I plug 1 into that, it's going to be 6 times minus 1 rather. 6 times minus 1 times e to the -1 squared, and that's my answer, minus 6e. Leave it in that form for me, please, if you have a question like this, right? Don't give me some decimal answer. I mean, yeah, there's a decimal answer for it. Oh, let me go back a second here. Let me go back. Oh, hold on. Can I do that here? Maybe I can. Let me see if I can. Yeah. Okay, so I guess I can. All right. So there is a decimal answer, but if I'm giving you a question, I'm going to want the exact form answer. So minus 6e is all I'm looking for on this. Obviously, minus 1 squared is still 1. So it's e to the power of 1. And 6 times minus 1 is minus 6. So there's your answer right there. That's the final answer. That's what I'm going to be looking for. All right. Let's keep going. The derivative of the natural log, just get this out of the way here. So we've done the derivative of the e to the x. And surprisingly, the derivative of e to the x is e to the x. Not hard to remember. However, the derivative of the log function, remember the log function is the inverse of it. The derivative of the log function, so if f of x is equal to the ln of x, then f prime of x is not just equal to ln of x, it's equal to 1 over x, right? As long as x is greater than 0. Why? Because the original function, being a log function, and hopefully you guys remember this from the stuff you did in advanced functions, you cannot take the log of a negative number. So you have to restrict the value of x from the original function, that it has to be positive. Never mind the fact that 1 over x is a rational function. I mean, that in itself has restrictions, but the fact is that the x has to be greater than 0 because the original function is a log function and you cannot take the log of a negative number. You can get a negative log, so the log of a number can be negative, but you can't take the log of a negative number. So just let me make sure that everybody's clear on that. A log can be negative, but you can't take the log of a negative number. So make sure that's clear in your mind. Okay, so let's do a few examples now of log, natural log. Later we can look at what happens when it's not a base e log. What happens when it's a base 2 log or some other base. But now we're just going to be looking at a base e log, right? So base e, of course, we said is a ln function. And the derivative of that we said is 1 over x. So let's differentiate now the ln of x to the power of 3. That's what we're going to try to do here. So it's another chain rule type of function. So the first step in that process, right, if you remember, is to treat this as if it's a function of a function. So if the function is the ln of x cubed, the inner function is x cubed, and the outer function is a ln of u, and we use the same du, dy, du times du, dx, then here's our answer. It's 1 over u times the 3x squared, meaning the derivative of this, 1 over u, so that's what the dy du is, right? Remember, it's 1 over. So it's 1 over u multiplied by the root of the inside function, which is the x cubed, and that would be 3x squared. So it's 1 over u times that. Well, the u, remember, is the x cubed, right? So it means that it's the 3x squared over x cubed, and then if you reduce that down, it's just simply 3 over x. Again, remember that the x has to be positive because the original function had to have a positive number that you're taking the log of. So that's one way to do it. Method 2, right? So hopefully that first method made sense. Do I need to go with that again, or is everybody okay with that first one? Let me go back very quickly for that, just to make sure everybody's okay with that. So I said that if I use the chain rule approach, then it would just be the dy du, where the u is equal to the x cubed. So that would be 1 over u, right? Because that's what the ln of if the ln of a function is, you take the 1 over that function. So 1 over u, and then multiply it by the inside function, which is 3x squared. So 3x squared over x cubed is 3 over x. Okay, there you go. All right, now let's take another approach to that. Recall the law of logs that states that, and this is something again from our work with advanced functions. There's something called the power law of logs. The law of logs states that the log base a of x to the power of n is n times the base a log of x. Let me just check with the room on that. Does that even look vaguely familiar? Have you seen this power law of logs before? Please say yes. Okay, you're supposed to have learned that in advanced functions. Okay, and I see Alexander saying yes, and I know that because I did teach him that in the advanced functions course. All right, the rest of you, I can't vouch for you, but I'm pretty sure that your teacher would have brought that up with you. Okay, good. So that's important to know, because if that is the case, then I could have written this function as the ln of x cubed as 3 ln x. I could have written it that way using this power law of logs. Don't remember that, Thomas? Yeah, well, that's okay. Well, that just so you know, that is the case. We need a, oh boy, okay. There's some assumed knowledge that we hope people picked up in advanced functions. So you're going to have to sort of try and plug those gaps as we go along now. All right. So that 3 could be put in the front. So we could rewrite the function, the ln of x cubed, as 3 ln x. We can rewrite it that way. And if that's the case, then the dy, and again, that 3 just goes on the side, right? That's just like that's just like a coefficient. The ln of x is just 1 over x. So you're going to have 3 times 1 over x, which is just 3 over x. Guess what? Same answer, right? I keep insisting that different methods don't give different answers. Okay, it's not like you are all going, and I keep using the same analogy. You're going to the Pickering Town Center and you chose different routes, but the destination is still Pickering Town Center. So whichever route you take, you're still going to end up in the same place unless you took the wrong route, in which case then yeah, you're not going to get the same answer because you went off in the wrong direction. But you're going to get the same answer if what you're doing is legit. And this is a legitimate way of looking at it. Change this thing from the law, because you can use a power law of logs principle, right? You can put that 3 in the front, and then you can just simply treat that 3 like a coefficient. The ln of x is simple, it's just 1 over x, so it's 3 times 1 over x. All right? Okay. Let's keep going. How about this one? The ln of 6x to the 5 over 3. I wonder if we could tackle this one. Why don't you give this a shot on your own? Let me give you a minute or two to come up with what you think the answer is, and then we'll go through the answer together as a class. Just remember now that the derivative of the ln is 1 over x, and treat this as if this was a function of a function type equation. All right, go through the steps with you here. The dy dx is 1 over u, right? So 1 over this thing multiplied by the root of the inside function. Here's the inside function right there. So that would mean that you have, if you put the u, which is the over 6x squared, that would be this thing here. If we multiply this out, this is what you're going to get when you reduce it down. 2 times 5 is 10. And then, of course, you're supposed to, you have the same base, so you're supposed to be able to subtract your exponents. So 2/3 minus 5/3, and that actually gives you x to the power of minus 1, of course, which means you can put the x at the bottom, and the 5 on top over 3x would therefore be the right answer. So Alexander is good to go. All right. Adam, 5 over 3x is good. Sarah, yes. Kushi wasn't so sure. Okay. All right. So we can see who is right and who is wrong there. It has to be simplified. Obviously, you have to simplify to its lowest terms, and there you go. Okay. All right. Okay. Anika is back. That's good. Okay. So that was one method. Here is another one. I'm just going to show you again that this could have been done a different way. Using the product, in the exponents, there's a product law as well, right? So the log of x plus y be equal to the log base a of x plus the log base a of y, as long as x and y are both the same. So what that means is I could have taken this function and expressed it as the sum of two functions, the ln of 6 plus the ln of 5 over 3. Right? I'm just showing you, different ways that you can make your life a little easier. That's all I'm doing. What we did before, maybe some of you actually did this. I don't know if you did. But if I took the ln of 6 plus the ln of 5 over, so remember, this is a product, right? What I'm pointing here is a product. I can split it apart by taking the ln of each of these things separately, right? And then adding them together. So the ln of 6 plus the ln of 5/3. So that's the function that I have split it up into, right? And the 5/3 here, yes, I can now take that and put that in the front using that same power law that we just talked about a few minutes ago. So if I did that, then here's my answer. Differentiating this, ln of 6, of course, that's a constant. Remember, it's just a number. Ln of 6 is just a number. And that's going to give me 0 plus 5/3 of 1 over x. Ln of x is 1 over x. So that's just 5 over 3x. I don't know if anybody tried that or thought of that. Maybe not. But you could have done it that way and probably got your answer even faster. Does that method make sense? Should I go over that again, or does that method make sense? All right, let me just do it again, just for the heck of it. I'll do it one more time. The product law of logs says that if I have a log of two functions, x and y, I can take the log, as long as it's the same base, of the first function and add it to the log of the second function if it's in the same base, as long as the x and the y are both greater than 0. They're both positive. So if I'm separating these two things, then I can take the ln of 6, which is a constant, plus the ln of 5 to the power of 1/3. Put that 5 1/3 in the front. We just talked about the power law a few minutes ago. And then it would just be simple. This goes to 0, right? So that's just 0. And this is 5/3 of 1 over x, which is 5 over 3x. Same answer. Nothing different about the answer, just a different approach. That's all. Okay. Connecting the derivative, let me get this out of the way here, of an exponential function to the slope of a tangent. All right. So this is the kind of thing you're going to have to be able to do as well. Determine the equation of the line that's a tangent to y equals x over x squared when x is equal to 2. So we've done this kind of thing before, not with exponential functions. We've done this before where we had an equation or a function, and we had to find the equation of its tangent line at a particular point. A line that just touches the edge of the function at that point, has a slope, has a y-intercept, and we can put it into a y equals mx plus b type format. So here we go. First thing, of course, I'm sure you know this, is I need to find the derivative of this function. So let's use the product law. Why am I saying the product law? Because I can write it like this, right? And I much prefer using the product law, generally, not all the time, much prefer using the product law rather than the other law, right? Which is the quotient law. So I'm going to approach this as if this is a product law question. So I'm taking, and we're back to deriving the e to the x again. Remember we did that a few minutes ago. So I'm going to take the derivative of the first part, e to the x by itself, times the underived second part, x to the minus 2. And then the derived second part, so minus 2x to the minus 1/3, times the underived first part. What do you think I'm going to do next? If I need to, well, the fact is that I just need to figure out what the function is when x equals to 2. So it's not as if I need to find where there's a horizontal tangent. So what do you think I need to do with my derivative in that case? Right, I have my derivative. What do I do with my derivative? Come on, folks. Need to get some responses here. I want to know the equation of the line, the tangent line, when x is equal to 2. No, I'm going to have to go with Adam on this one, not Sarah. Sorry, Sarah. Only time I want to set it equal to 0 is if I'm trying to get a horizontal tangent. But I'm not trying to get a horizontal tangent this time. What I'm trying to get is the equation of a line at for a tangent line when x is 2. Do you see why we're saying that, Sarah? And by the way, I appreciate the fact that Sarah gave a response. That's better than the people who didn't give a response. Okay, so Sarah, I commend you for that. Let me just make sure I say that. So what we need to do is plug in the 2 into this function. Okay, so the dy dx is equal to this. And yeah, we just put it into a form which is probably easier to work with, which is this. And I'm putting in, and you know, in a case where you just had to plug in the 2, it wasn't a complete necessary to do this, but it's a good idea for you to simplify these things as much as possible. And I'm going to put in the 2 into this, right? If you factored out the e to the x out of this, you would get x minus 2, right? So if you factor that out, And if I put 2 into that now, so again, all we're doing here is just simplifying the expression. Just simplifying the expression. That's all we've done so far. Clearly, if I put 2 into that, when x is equal to 2, the slope is actually 0. Right? Putting 2 into this, right, gives me x minus 2, or 2 minus 2, which is 0. 0 times anything is just going to be 0. So when x is equal to 2, the slope is 0. So I now know what the slope of the line is that I am using, right? But I need more than the slope. I need to know where this line crosses the y-axis for me to get the equation of the line. It's a horizontal line, that's true. It's absolutely horizontal line. So what do you think we need to do next, class? Right? How am I going to figure out the rest of the equation of the line? It's going to be a y equals some number. Hopefully that makes sense. It's a horizontal line. So it's just like you have a horizontal line at y equals 2. It's just a horizontal line that goes through 2. I now know that this line is a horizontal line. Slope is 0 when I put in 2. Set it equal to 0 now. No, I wouldn't do that. I wouldn't do that. Because I've already figured out that when I set it equal to 0, I'm going to get that x is 2. I know that. So I need something else on it. And Adam, by the way, thank you for at least having a response. Give me something else, though. Give me something else. I need to know. Remember, if it's a horizontal line, it's going to end up being y equals something. That's how horizontal lines are written. Y equals mx plus b. Okay, but what's the slope, Javier? What did we just figure out the slope was? 0. Okay. So y equals b then. But then what do we do to get this? Exactly, Adam. Exactly. So where is this elusive b? That's the question I'm asking. Right? What is y equal? What is this horizontal line? Put 2 into, okay. Okay, so f of 2. Thank you very much, Sarah. Thank you very much, Adam. Right? You need to put that 2 into it's 2 that gives you this 0, right? This horizontal line. That's a fact. But what is the value of the function at 2? That's really what we need to find out. Because that will give you what the horizontal, what the y equals is at. So we need to put 2 into the function. That's exactly right. So let's do that. So it's a coordinate at the point of tangency when x is equal to 2. So let's put 2 into the function. So here's the original function. E to the x squared. So e would be 2. Sorry, x would be 2. So e to the power of 2. And then the x squared would be 2 squared, which is 4. This is the way I'd like you to put that answer. Right? That's according to the point of tangency, f of 2. And then, since the slope is 0 of the line, there's my equation. Y is equal to e squared over 4. Again, I want this to be an exact answer. Right? Whenever you, if it's possible, not always possible. If it is possible at all, I want these things to be exact answers, such as the one that you just saw me write. Y is equal to e squared over 4.